Welcome, everyone, and good afternoon. So this presentation, the reason why I created this specific topic, it comes a little bit back to the current situation. Distributed denial of service has been around since the beginning of the internet, actually almost before the internet was created. But the thing is, we're constantly seeing new attack vectors, new types of attacks there. We're seeing more of them, they're more frequent, they're more complex, and so on. And there are a number of reasons for this, and that is basically what this presentation is about. So let me show you the agenda. So first of all, I'll give a brief introduction into the current DDoS attack trends, because that basically is the baseline for the presentation itself. Then I'll start touching on two areas which are extremely important when you think about distributed denial of service. Number one is the protocols themselves, the protocols we're using on the internet. And yes, many of them are really, really bad from a security perspective. My good friend Eric, he explained this from an IPv6 perspective this morning, but there are so many, well, let's use the word crazy designs out there. And I'll try to explain what the problems are and how we can try to solve those issues. The second thing is DDoS resistant network design. And that also comes back to, there are a lot of things you can do to harden your network from a DDoS perspective. And unfortunately, not many people are doing this. So I'll go through the common pitfalls, explain what you can do, and hopefully that will help you to understand what the problems are, how to defend against those, and how we can all work together to make the internet a more secure place. So first of all, recent attack trends, and I'm just pointing out that we published our latest threat intelligence report. The link is on the page, and that gives you all the details about what I'll be saying. So I'll be brief. I'll go just touch on highlights, but if you want more information, then you can take a look at this link down there. So first of all, key findings. In 2020, we saw more than 10 million DDoS attacks, and which is a 20% increase year over year. 10 million is a lot, because that means we're seeing more than 800,000 attacks per month, and which is actually more than about 130,000 attacks per month on average. It also means that during this talk, then there will be around 740 attacks on the internet. And yes, it's constantly happening, and it's really, really impactful. Also, last year we got 4 new attack vectors, which attackers began to use. In 2019, we saw 7 new. And yes, now in 2021, we are seeing even more appearing. That will be published in the next threat report or in our threat advisories. So we're constantly seeing new attack vectors. I'll come back to it a little bit later on. And also, what happened last year is extortion, DDoS extortion. It is somewhat similar to ransomware. That is, someone takes over your computers and then you have to pay money to unlock them. So this guy, guy / organization / group, hacker group, we're not exactly sure who those were. They launched attacks against 275 different organizations in 40 distinct industries across 55 countries. So basically, they launched an attack. In most cases, they took down the services, website, or whatever of the company, sent an email then and saying, please pay us money or we'll continue attacking you. And in about 50% of the cases, they continued attacking until either, they got money. We haven't got any information about someone actually paid. And I really hope people didn't pay, because you know what, if you pay money to criminals, they'll just continue. That's how they work. The attacks were mitigated. So let's take a look at the attack vectors. So we came up with this. It looks very similar to the periodic table. The reason why we created this is makes it easier to understand which attack vectors are more impactful and how they work. And if you take a close look at the one here on the left-hand side, PMSSDP, which is Plex Media SSDP, then this one tries to show how the risk, basically how many vulnerable devices are on the internet, which can be used to launch these attacks. And then you see the amplification factor over here. But very briefly, the attack vectors we saw last year were RDP over UDP, basically like Microsoft remote desktop running across on UDP. And we managed to find about 33,000 devices on the internet which could be used as attackers. And we saw attacks up to 750 gigs. Same with Plex Media. Many people use Plex at home, but that was also used as an amplification factor. Same with DTLS, we'll come back to that one, and Jenkins, which is used in data center deployments. And this is what I will be covering a little bit more detail, because basically every protocol, if it's not secured properly, can be used as an attack vector. So if we, regarding the attack vectors which were used last year, then DNS is at the top. And in second and third place are TCP attacks. And this actually changed, because previously TCP type attacks were at number 1. But because of the weaponization of the attack vectors, and also because people, especially students, were staying a lot at home, then the attacks against schools and educational organizations increased. Basically, you're at school, you were supposed to be sitting at home, attending remote education across the internet, and if you didn't want to join, then basically you went to a boot distressor service and launched the DDoS attacks against your school. No school. So that, and DNS is extremely effective as an attack vector. I'll come back to that a little bit later on. Also, another trend we saw is the number of attacks which are using multiple attack vectors. Multiple meaning up to 25. So if you were being hit with a DDoS attack, instead of just being hit with a DNS flood or a NTP flood, then we were seeing attacks where they had up to 25 different attacks combined into one, meaning stopping those can be really complex. And as soon as you stopped one attack vector, then basically another one popped up. So that basically led me to thinking we need to start doing something about all this. Okay, I work for a company which makes a living of selling DDoS mitigation devices, but this is not good. We need to educate people about what can be done, and so we can get rid of this and do something better than just filling the internet with attack traffic. So the trends which concern me is we're constantly seeing new attack vectors. Multi-vector DDoS attacks, as I just explained, more complex attacks which are more difficult to mitigate, and then forgetting best current practices. And the statement at the bottom, I'll come back to that a little bit later on, but basically improper network design is contributing to the attacks. So instead of having your network design helping you to be resistant, then some of them are actually helping to make the attack more effective, and that is not a good thing. So let's look at the protocols. So first of all, what are the main issues regarding the protocols we're using on the internet? And the biggest one is, of course, the lack of universal source address validation. And now we're talking about spoofing. Basically, there's nothing stopping you from creating a spoofed packet that's basically changing the source IP address in the packets you're sending out to the internet, such that it looks like it's coming from someone else. And the reason why you would do that is if I send a ping to someone and I spoof the source IP, then the response to that packet will go to the victim. Basically, it's being reflected, and that's the reason why we're talking about reflection type attacks. The second thing is the amplification. You send one packet, and the goal is basically to get a large packet back, either one large packet or multiple large packets back, meaning you're amplifying your attack. So instead of spending a lot of resources to create large packets and then sending them to the destination, which is basically UDP flooding, you can then send a lot of small packets to someone, and or a lot of someone's, and they will then create large packets and send them to the victim itself. So basically, you're making your attack more effective and increase the size of it. And the third thing is intra versus inter network protocols. And we've been seeing a lot of this. Someone creates a protocol or a service which is designed to be used internally, like inside the data center. I'll talk about Memcasting a little bit afterwards. But that is a service which, when it was created, the designers thought, nah, this will always be internal. There's no reason for security because no one will be able to abuse it from the outside. But then we got cloud. And then everything started to move into the cloud or into virtual data centers. And all those protocols where the designer thought they would be internal, they are now suddenly out on the open internet. It basically means there are no longer intra-network protocols. Everything is on the internet these days. Let me give you two examples. And first of all, let's talk about Memcasting. This is an extremely good example of a protocol/service which people believe that would only be used internally in secure data centers. It's been around a bit, but it's a very good example. So Memcasting is a distributed memory caching system, which is usually used as a caching layer between front and backend systems. Could be SQL, could be web services, and so on and so on. And the original design allowed anyone to communicate with it on UDP port 11.2.11, meaning you could actually spoof the source IP of your packets. And the commands, some of the commands which you could use are things like stats. Basically, you send the query and saying, hey, please tell me everything about what you've been doing for the last 1 hour, your caching percentage, and so on and so on. There's another command called get for a specific object. So you say, hey, could you please give me this object with a name? And you can create objects using the set commands and then the append commands to append to the objects which exist from before. And if you start to think about this from a security perspective, and also that this is sitting on the open internet where anyone can spoof the packets, what can possibly go wrong? So let's go into that. So if we look at how we can abuse this, this basically means that anyone can now issue the set commands and the append commands across the internet and basically create objects up to 1 megabyte in size, not 1 megabyte. That's a lot. That's a rather big object. Then you can now do is to send a spoofed UDP packet containing the get command. So first I'll create the objects, and then I'll do send the get command, and I'll spoof the source IP. So instead of going to me, it will go to my victim. If the guy is clever, he creates the objects with using a short name, like, for example, the letter A. That's a very short one. And then you create the get packet. And the maximum payload size for Memcasting packet is 1400 bytes, which means you can create a single spoofed request with the get command, and then just type in the letter A up to 729 times. So what will happen is the Memcasting server will now receives the command and says, oh, you want me to send the object A 729 times to you? Of course, I'll do that. And will then generate 536,302 packets of size 1442 bytes and send them to the victim, which gives a theoretical amplification factor of 500,000 to 1, but due to some specific implementation factors, this is only 51,200 to 1. And I think this picture basically explains the problem. And if your destination is, if that sending a single packet is not enough to take you to destination, then you send 2 packets, or 3, or 1,000, and so on. Basically, you understand where I'm going with this. This is just totally, absolutely crazy. Luckily, this is the number of vulnerable Memcasting servers in the internet has been dramatically reduced because of most of them run in data centers, and most of the people out there realized, this is not good. So they have been secured, and also the Memcasting protocol has been updated and no longer talks to UDP. But there are still some Memcasting servers out there. The second thing, DNS, like I said, it's the most popular attack vector today. And the reason for this is, you can see it up here, it is basically the phone book of the internet. It is designed to be hierarchical, decentralized, very effective, very good. But the thing is, it can be abused if you do not. If the guys who are running those servers do not secure them properly, they can be abused. So you can use them. You can send spoofed queries to recursive servers saying, "Hey, what's the? Give me information about this specific domain name," and then have the reply sent to your destination. You can attack the authoritative service by using attacks like water torture attacks, and so on and so on. There are many different ways to abuse the DNS protocol. And it is UDP, and it can be secured, but you actually have to do the right thing. So let's go back to the basics. Try to understand what the problems are and how we can solve those. So first of all, what is actually spoofing if we go into the details? Because when we are communicating with someone, how do we communicate? It's usually bi-directional. We greet each other. That means we can then understand that the other side is willing and capable of communication, and then the flow of data starts. Like I come in and say hello, and then the other guy says hello, and then I'll say my name is Steinthor, and the other guy says my name is Lucas, and then I ask him, are you enjoying this conference? And he says, of course, and he really likes the DDoS talk. So, but the reason why I'm going back to basics is I'm trying to make a point here. We usually, when we talk to someone, we validate who we're talking to. Also, amplification. If we look at it from this perspective, I meet the other guy and I say, hello, I'm Lucas. Actually, I'm lying. I'm not Lucas, I'm Steinthor, but I'm pretending to be Lucas. And if I'm talking to a service which sends large replies, then the reply could be something like this. Hi, Lucas, my name is Service, and he sends it, basically tells me the entire life history of his service and all kinds of things. But I'm not responding. So basically, the service will say, hello, doesn't get any kind of response and continues. So what are the problems with this? If we think about this like a protocol, number one, you need to verify that you're talking to a real person, that the other side is willing to talk to you and is capable of talking to you. And as I said, the other guy could be using a spoofed IP. Number two, don't send large replies until you have done your validation. That's extremely important. So, and also if you don't get replies, just don't continue to repeat what you're saying multiple times. And the reason why I'm making this point is we have services on the internet which not only reply 2 extra times and then timeout, they continue sending the replies multiple times. And actually, there was one service on the internet which someone was scanning the internet, and they pinged it with a spoof, pinged it, and that service continued to is still sending replies. 4 years later, it's still trying to send those packets to the destination. So no timeout in that specific case. So when implementing protocols, don't repeat too many times and use increasing loud timers and then timeout at some point in time. But now you are probably thinking, wait a second, why don't we just ban source address spoofing on the internet? Well, that is actually a very valid question. And you are totally correct in thinking if we would not be able to create spoofed packets on the internet, there would be no reflection attacks on the internet. We would basically have solved the entire problem. And you're totally correct. But we've been trying to do this since the beginning of the internet. And the CIDA is an organization, a research organization, which is looking at various aspects of the internet and researching them. And they have been tracking this for many years, and they have a service where you can go in and look at the current status. And the current status is that 39.1% of all the ASNs, that means organizations like service providers and corporations, allow the transmission of spoofed packets. 22.1% of the CIDR blocks, that is the subnets on the internet, which have been allocated, they allow spoofed packets. And coming back to my friend Eric, then the situation for IPv6 is actually worse. Well, not almost as bad. It's 34.7%. So we have spoofing on the internet across in many places. Europe and the US is in pretty good shape. The problem is, as long as you have one organization on the internet which allows spoofing, that can be used to host attack services which then spoof packets of someone else. So we need to work together to solve this. So first of all, take a look at BCP 38, which is on the right-hand corner up there. That was actually published in May 2000, which explains how to solve this. So the information about how to solve this has been out there for 21 years. But still, I took a look at my old notes, and in March 2018, the percentage of IPv4 ASNs along spoofed packets was 31.4%. So we're getting worse at this. We're not getting better, we're getting worse. And that is not good. So how, if we cannot forbid these people from sending spoofed packets, then what can we do? And the answer is cookies. So I'm not talking about browser cookies, I'm talking about protocol cookies. And handing out cookies to clients, this has actually been around since 1996. And again, I have the link for you up there, which explains the design of how to do this. So this has been around for 25 years, and people are still not doing this correctly. But the basic idea is, if a client connects and does not have a cookie, give him a cookie. But that cookie should, of course, be unique and apply to that client only, should only be valid for a certain time, and so on and so on, and should be easy to generate and not use much resources when generating this. Basically, you connect, and the client connects, you give him a cookie, and then you forget about that client. If the client connects again, then and gives you a cookie, then you need to give you the cookie you just gave to him. You need to validate it, make sure it's okay, and then you start talking to him. So let's take a look at how this actually works in practice. So RFC 6347, that is TLS across UDP, explains how this should be done. So this is a YSEC capture I did in my lab. And here we have a client which sends a client hello, basically says, hey, here I am. And the size of that packet is 274 bytes. The server responds with a small packet, hello verify request, which contains a cookie, but the total size of the packet is 90 bytes. So actually the first reply from the server is tiny. It is smaller than what the client is sending. So there's absolutely no reason whatsoever for someone to try to abuse this. It doesn't get anything out of it. It takes more CPU resources and memory to create the original client than and try to use this as an amplifier. It doesn't make sense. So as you see on the screen, the server created the cookie. The client will now connect again with using the client hello, but now it has the cookie it just got from the server. The server will now validate this and begin talking. And as you see in this specific case, the server will now send a server hello, which includes the certificate and all kinds of things. And it's multiple packets, it's large, but that's good. You know you're talking to a real client. But if you take a look at the RFC in detail, then it says, when the client sends its client hello message to the server may respond with a hello verify request. It doesn't say should, in my opinion, it should have done that. And yes, there are implementations out there which implement DTLS 1.2 without doing the hello verify request. And that is actually the reason why DTLS actually made its way into an abusable attack vector last year. And a certain company, which I'll not name, got its name all over the internet because its servers were collapsing left and right because of this issue. So the protocol has everything was needed, but the implementation was purposely not implemented without doing a hello verify, mandating a hello verify request. So what I'm trying to say is there are ways to do things properly, but please do them in the right way and do not make it optional for the clients to go through the validation process. Also, another thing you should think about is serverless architecture and protocols. now we're moving everything into the cloud. We're creating microservices. We want to have scalability. We want to be able to have a service which is running with minimal resources, but auto scale to larger deployments when needed, and then scale down again when the load decreases and so on. But for that to work properly, the protocols should be built such that you store minimal state on the servers and on the network devices, because this will help you to do the scaling. And if you do this correctly, and I repeat that, correctly, then you can actually benefit a lot from this. But there are many pitfalls, so you need to be careful a little bit. But a good protocol design can help you to do this well and make your new fancy microservice / cloud architecture secure as well, which is a good thing. Okay, I could say a lot more about protocol designs and a lot about mistakes and how to learn from them, but we only have limited time, so I'll go over to the DDoS-resistant network design. So these are the top 4 issues we've been seeing in the last years. So understand your network, do separation of inbound and outbound network traffic. People are relying on stateful devices and then assuming your attacks are only coming from outside the network. So let's jump into this. So understand your network before the attack hits you. And people are probably thinking, why? Why do you need this? Because when the attack is hitting your network, everything is collapsing. Then you need to be able to, in some cases, if the network is not built properly, you need to do changes on it. You need to shut down services. You need to move things around. Then you need up-to-date documentation in the architecture. You need to understand which devices you have, where they're located. And I've seen multiple instances of people saying, I don't really know where the traffic is coming from. Is it coming from this link or that link, or do I have a dual path or not? Have those things in place before the attack hits you. And then also remember that there are 3 types of traffic on every network. Legitimate, that is things which should be there. Illegitimate, that is bad things which should not be there. And things which you do not have a clue. It could be good, could be bad, but you need to be able to determine what it is. And you also need to understand what are your normal values? What should you be seeing? What's expected bandwidth? What's the expected packet per second? Transactions per second? Where are your clients coming from? What are the expected TTL values? All that information can really help you when you're trying to understand what is good, what is bad, and what you can possibly throw away when the attack is hitting you. Also, separation of externally and internally originated traffic. And the reason for that is in many cases, we've seen designs where you have web services which are getting inbound traffic, and then you have other those same services are maybe communicating with external services and using the same link, or your internal clients are using the same links as your other services. And then it can be really difficult to implement access control lists or something when the attack is hitting you, because then you run the risk of taking down your VPN services when you're trying to stop an inbound attack or something. Please separate things. And here's an example of how you can implement. Here's a good example of how you could possibly do this. Build a network design such that you can defend against the most common attack vectors. So if we go quickly through this, then let's assume you have a web service, and your clients are communicating on port 443, basically normal TLS. So then that should be isolated. Isolation, yes, if possible, do physical links. If not, that's because that's a little expensive. Then at least do VLANs. Minimal, do at least subnets. So isolate them with subnets. So please if you do that, then you can implement access control lists, which basically say only port 443 should go to the web service and absolutely nothing else. No DNS, no NTP, no crazy reflected amplification type of vector which is trying to hit this. If you do that, it makes your life easier. But if you need to, let's assume that you want to be able to go out on the internet to get DNS information. Well, most people do that. So then you do two things. You set up a caching server internally, and then you have a recursive DNS which goes out. But that should only go out on destination 53 and nothing else. And you should only accept replies on which are coming from source IP, the source port 53. What I'm trying to say, make this as strict as possible. If you have an authoritative DNS server, then you should have a caching server in front of it, because that will reduce the load on the authoritative server. No one should talk directly to it. And then the same thing, implement strict access controllers, so only the correct things can go out and only the correct responses can go in. And if your internal users want to go out on the internet, force them to go through a proxy and make sure that only replies to the proxy IP are allowed in. And the reason for that, if you do it like this, then you've actually killed one attack vector called TCP SYNAC attacks. Because what people many times do is launch TCP SYNAC plots against web services. But if you have no sessions originating outbound from your web service, and we've actually made sure that with this design that will never happen, then you can basically block all inbound TCP SYNACs. So with a good design, you make your life easier and you actually block many attack vectors which are used today. You will not block them all, but it'll make it easier for you to stop attacks from those if someone uses those vectors, if you have a good design. Okay, so now someone is thinking, interesting, this makes sense. Now I'll go to my firewall and implement those things. Then we take a look at this thing. We do a survey of our customers every year, and where we ask them, what have you been experiencing last year? And in 2020, then 83% of enterprises which got hit by an DDoS attack, they told us that their firewalls or VPN concentrators contributed to the outage. Basically saying, they get hit by an attack, and the firewalls and concentrators, basically, they did not stop the attack. They made the attack worse because they basically collapsed and died. They didn't help in any way. So in this specific case, we're saying in 17% of the cases, the firewall did not die. Is that a good design? No. The reason for this is because those devices are stateful. They are tracking connections. They're tracking state, using up CPU and memory. And if you get hit by a large DDoS attacks, those devices will, in almost all cases, 83% of the case, die. So they can be worse than nothing in many cases. And if we take a look at the how things have been evolving during the years, we did the same survey. We've been doing the survey every year for a long time. In 2010, about 50% of enterprises told us this story. 2016, more than 50%. Last year, 83%. So basically, this is getting worse. And the designs of today are less DDoS resistant than what we had 11 years ago, and that is not good. So what can you do? So this is a typical design. We have a web service with a load balancer in front of it. We have DNS services. We have a firewall and the router in front of it. And basically the firewall is sitting there and trying to control things. So what I'm saying is, instead of using this type of design, then we know we can basically do everything on the router. I'm not saying that the firewall is useless. Firewalls are really good when you want to understand basically the contents of the packets themselves and when you want to do more complex things. In this specific case, the only thing we're doing is sending TCP packets with destination port 80 or 443 to the load balancer, which then sends it to the web services. That's it. We do not need any kind of state or CPU or memory to do that. It's stateless. It runs at line speeds, has no impact on the router, and that means there's no impact if you get hit by a DDoS attack. Yes, of course, the attack will have to be mitigated, but at least the firewall is not collapsing. The same thing for DNS. Pyramid Protocol UDP and destination port 53, same thing. You have other authoritative DNS services. That means the only things which should be sent there is UDP with packets with destination port 53, and that's it. no firewalls. And at least this will help you by not having your stateful devices collapsing and dying. So, but what about internally originated attacks? And Eric mentioned this earlier today. So DDoS attacks can originate from the inside of your network. So there are two cases. That is when infected devices are on the inside of your network. That could be an IoT device, it could be a PC, which has been hijacked to be used as a bot and is now being used to launch outbound DDoS attacks. And remember all those stateful devices? Will they survive if you suddenly get an outbound DDoS attack coming from inside your network and going out your firewalls? Probably not. So keep that in mind. There's also another aspect is if an attacker really wants to take you down, then maybe he will attempt to take control of a device inside your network and then use that device to launch attacks against the services from inside. And yes, there have been cases of someone doing that. We have had customers with really good designs which are following the best practices, but they got taken out because the attacker took control of devices inside their networks and used them to basically bypass all the defenses. So keep this in mind. So, but this is another thing which we've also seen and which you also need to think about is recovering after attacks. So there are two cases. You get hit with let's say you're running a web service and the average you have about 5,000 clients talking to you at any one time, and someone launches a DDoS attack against you. Everything goes sideways, your service is interrupted and so on and so on, but you manage to fix it. But then the thing is, those 5,000 clients are probably hammering on your firewall with TCP SYNs, and that can actually look like a TCP SYN attack. And the load of the legitimate clients all trying to connect to you at the same time can actually be enough to take down your services again. So make sure your design can actually survive the flood of legitimate clients connecting to you. But there have also been cases where the network protocols or the network design also collapses when you get new clients. And I actually have one interesting case for this. We had a financial service, and they were using VPN. All their clients, which were organizations, connected using VPN clients, and they built a VPN cluster, which was designed to accommodate up to 5,000 simultaneous connections. And that looked good. They tested building this up, everything looked good. And then they thought, okay, let's see what happens if we have a power failure or if everything gets taken down by a DDoS attack or something. So basically they just pulled the plug and then the clients started to reconnect. But as I said, it was a VPN cluster, and the design of this VPN service was such that every client had to connect to the cluster leader, and then the cluster leader sent the clients to the individual VPN devices. And that became a bottleneck. So basically, instead of taking approximately 2 to 3 minutes for all the clients to reconnect and everything coming up, it took 5 hours for all the clients to reconnect, because all 5,000 came in at the same time. The cluster leader basically couldn't handle more than 5 connections, new connections per second. So they got timeouts and everything basically, went sideways again. So think about these things. It's not enough to be able to resist the attack. Make your design such that it can recover gracefully when the services are reestablished. So coming to my summary. So basically, first of all, do source address validation. If you're a normal person, there's not much you can do, but at least if you go to the Kaida web service, you can download a test tool, which will then test if you are capable of, if your service provider is doing source address validation properly. And if not, complain to him, because everyone should be doing this. The less source address spoofing we have on the internet, the better. The second thing, if you are responsible for creating new protocols or services, make sure you validate to whom you're talking. Don't send large replies until the connection has been established, and think about reducing protocol state as much as possible. Also, follow the BCPs, understand your network, try to do separation of traffic, reduce reliance on stateful devices. Yes, they have a purpose, but not as the first thing which will get hit by a DDoS attack. They will collapse and die. And make sure your services recover gracefully. And here's an important thing. Get your security guys, the networking and server teams and your developers talking together. Like coming back to the Memcasting example. It's a good design for what it's designed to be doing. But the Memcasting solution is not designed to be on the open internet, but someone moved it out there. And that's the reason why it was abused in this way. If someone had done a security review from the perspective this could potentially be on the open internet, it would not have gone through. So have your people talk together, because then you can avoid making the same mistakes as people have been doing for the last 30 years. And I think actually this comment is really, really appropriate in this case. Learn from the mistakes of others. You can't live long enough to make them all for yourself. And as we've been seeing, the trend is going in the wrong direction. People are doing the same, making the same mistakes as we, the old guys in the industry, have been doing for the last 20 years. Please don't continue doing the same mistakes. Learn from it and try to help to make the internet a more safer place. So thank you for your attention, and I'll hand over to you guys on the stage. Thanks.